All right, students, in this video, what we're going to do is we're going to apply some of the concepts that we learned last time when we learned what an ideal gas is, and we're going to actually start using some of those simplifying assumptions to solve problems dealing with ideal gases, and you'll see how useful this equation of state or the ideal gas law is once we start doing that, okay? Just going to start the video by defining to you what this is, what the equation of state is, which is also called the ideal gas law. It's simply PV equals nRT, which you've seen before and I've alluded to in a previous video. It's a thermodynamic equation describing the state of matter under certain conditions, okay? So P is always pressure, V is always volume, T is always temperature, N is the number of moles of the gas, and R is just a constant, which is 8.31 with those units, okay? All right, so this is very, very, very important because if we have a particular volume or a particular sample of gas and we do different things to it, okay, like change the volume while keeping the temperature constant and so forth, we can actually come up with numeric values for what the pressure would be. And so what is really important here is that we need to think about what's happening when a thermodynamic process occurs. So typically with our applications of the ideal gas law, we start with initial conditions and we're asked to find final conditions, and usually I just call initial conditions subscript 1 and final conditions subscript 2. You can do it however you want, but that's how I'm going to do it when I do my problem solving. Okay? So, also called the ideal gas law, we have to assume the gas behaves as an ideal gas. That's what the whole equation is based upon. Okay? All right. Now remember that molecules actually move in a random motion within the container at a range of speeds. All right? This is actually problematic when it comes to considering quantities that involve the velocities or speeds of molecules. Okay? And I have to introduce to you or mention this idea of the Boltzmann equation. And what this is it's a description of the statistical behavior of a thermodynamic system that's not in equilibrium. Okay, so turns out that the average kinetic energy, which is 1/2 mv bar squared, it's also equal to 3/2 k times t. So here you go, you have your average kinetic energy being directly proportional to temperature, which is what I've been alluding to all the time in this topic. Well, here's your constant of proportionality. It's 3/2 k, where k is this particular constant right here. And v bar is actually not the average velocity, the average speed. It's called the root mean square speed. I'm going to talk about what that means in just a second. Okay, the root mean square speed is actually, well, it's called the RMS speed. It's actually close to the average speed, but it's actually not the same as the average speed. Okay, you can see this. What it is, and I'll do an example in the next slide, is what you do is you square each individual speed, add them together, and then divide by the total number. Okay, does that make sense? So if you wanted to find the root mean squared speed, you would actually then take the square root of that entire number. Okay, and I want to also point out that k here is this value r, which is the previous 8.31 constant divided by Avogadro's number. Okay, that will be obvious to you later, although really we don't do a lot of equations using k. Our version of the ideal gas law in this class, we use PV equals nRT. Okay? Okay, so as an example of the root mean squared, okay, I have 4 molecules, and they each have these speeds, okay? The average speed, well, that's very, very easy. That's adding them up and dividing them by 4. What's the RMS speed? Well, what it is it's the square root of each of them squared divided by 4. So you can see that the number is similar, but it's not exactly the same. Now, you're not going to be required to necessarily find the root mean squared value of anything in this class, maybe in a lab, which I'll guide you. But I'm telling you this because this is very, very important. The whole idea about thermodynamics, because it's a microscopic study of physics, it's really, really based on statistics. So the idea of an RMS speed or an RMS value is very statistically based. And why is it based on statistics? It's because we can't really think of thermal physics and gases and things on a molecule by molecule basis because we don't really know exactly what's happening with each of them. So it's a macroscopic study, and really the ideal gas law, the kinetic theory, takes something microscopic and it puts it in a macroscopic fashion where we can actually use the ideal gas law to solve problems. That's kind of an underlying theme in this topic. Okay, so the ideal gas law tells us that there are four main variables that determine how a gas behaves: pressure, volume, temperature, and the number of moles. Okay, so when we're doing the simulations, you know, all of these, you have to know certain conditions, and you know, with PV equals nRT, you've got basically now you've got four variables that you can change, right? You cannot solve a system of equations you can't deal with four unknowns, okay? You have to keep certain things constant and then investigate how two particular variables change in order to get something meaningful, okay? So what we're going to do, I'm going to talk about specific gas laws. What we're going to do is we're going to assume that the number of moles stays the same almost all the time. We're going to really only be concerned with pressure, volume, and temperature. Changing any of them affects the others, okay? So case number one, I'm going to hold V and N constant, and I'm going to investigate how T and P change. Remember, if I did not hold V constant or N constant, I would have four changing variables, and it would be impossible to tell how one affects the other. Okay, so I have to hold certain things constant to be able to do some physics here. Okay, so I'm holding V and N constant, and I'm changing T and P. Now, I can change the temperature by putting it in an ice bath, or adding heat or whatever. Okay. Now, how do you think that T and P are related to one another? Okay. Well, it turns out that you may have surmised this: as T gets greater, P gets greater, and as T decreases, P decreases. And this is called Gay-Lussac's law. Okay. So again, if you hold V constant, then you have a direct relationship, proportionality between T and P. Okay. So turns out that T is proportional to P, or exactly T is equal to K times P. This is a very important relationship right here. Okay. So if I start at state 1, T1, P1, and V1, and I go to state 2, T2, P2, and V1, notice how V does not change, I can make this relationship P1 over T1 equals P2 over T2. And that is an application of the ideal gas law to solve a problem using Gay-Lussac's law. Okay. Now, P and T clearly have a linear relationship when V is held constant, and the slope would give you, experimentally, the constant of K, which is 1.38 times 10 to the minus 23. What a nice lab that would be, right? Okay. Okay. So experimental data under constant V conditions might look like this. You extrapolate this line back to negative 273. If you're dealing with Kelvin, it would go through the origin. Okay. Remember that absolute zero refers to the complete absence of any molecular motion. That is not possible because that would mean zero pressure and zero volume. This is how the Kelvin scale was developed. This number 273, which is actually 273.15 as a conversion factor between Celsius and Kelvin, it's actually developed not because we ever got to 0 Kelvin, we haven't, but by extrapolating experimental data. It's kind of interesting. Okay, here's an example using this particular the Gay-Lussac's law for the ideal gas law. Go ahead and try this one. Okay, so the way that I solve these problems, I always set them up like this. I always put down what I know and what I don't know. I put all the initial conditions in the first column and the final condition, or the final state, in the second column. I always rewrite the ideal gas law and then solve it, right? So in this case, because we're holding the volume constant, I just rearrange for P and T. NR over V is all a constant, so I don't actually really care about it, because I'm going to say the ratio of P1 to T1 is equal to the ratio of P2 to T2, and I solve for P2, which is 3.7 atmospheres. Pretty cool. Okay, so case number 2, I'm going to now investigate volume and temperature by holding the pressure constant. Okay, all right. So what happens? What do you think is going to happen to the temperature of a sample if you decrease the volume, in this particular case right now, while holding P and N constant? Okay, correct. If you said that the temperature goes up as the volume goes up and goes down as the volume goes down. Okay, all right, and this is called Charles's law. All right, so if you hold the pressure constant, then V is proportional to T, and V equals K times T exactly. Okay, so again, state 1, T1 V1 at P1, state 2 T2 V2 at P1. We have the simple relationship that V1 over T1 is equal to the ratio of V2 over T2 as before, using P and T. Okay, so again, V and T have a linear relationship, and again, this is just like the previous case. The slope of this particular line would be the actual constant K. All right. The experimental data would be something like this. All right. So very, very similar argument to what we talked about before. Absolute zero would mean zero volume, which of course is not possible. If something has zero volume, then it doesn't really exist. Okay. All right. Try this example of an application of Charles's law. Okay, so my initial conditions, my final conditions, I'm trying to find T2. I'm rewriting my ideal gas law. Okay, V over T, V1, T1, V2, T2. I solve for T2, I get 590K. Okay, it's very important here to note that when you're using the ideal gas law, you need to use Kelvin instead of degrees Celsius. Okay, all right. The final case, I'm going to investigate V and P while holding the temperature and the number of moles constant. Okay. All right, and this is called Boyle's law. So if you hold T constant, then it turns out that, and if you look at this demo and play around with it a little bit, you can surmise this. As the volume goes down, the pressure must go up. And why is that? Because it's the frequency with which the molecules collide with the walls of the container will increase. Okay, this is going to be a slightly more difficult situation. Okay. P is proportional now to 1 over the volume, or P times V equals that magical constant K. So at state 1, again, P1, V1 at T1. State 2, P2, V2 at T1. It turns out that P1, V1 is equal to the product of P2, V2 by the same logic that I've been applying before. Okay, P and V now have an inverse relationship. So if you graph them, you're not going to get a straight line, but if you graph P against 1 over V, you will get a nice straight line. And I'll leave it up to you to think about which of these would give you the variable K, or how you would get K from that. Okay? Okay, as an example of Boyle's law, try this one. Okay, so here's my initial, my final, okay? P1, V1, P2, V2. I just solved for V2. So you see the algebra here is really not that difficult. I get 0.3 liters from my volume. Okay? Okay, so if we put everything together, we have 3 cases, all keeping n constant. Number 1, we have T is proportional to P, giving this particular case, and that's keeping V constant. Number 2, V is proportional to T, keeping P constant. This case, this is a very important slide because I'm summing up all the ways in which we use the ideal gas law to solve problems. The product of P and V equals a constant, keeping T constant, giving this relationship right here. Okay, if we put them all together, we get PV over T equals a constant. Okay, and I'm going to say that constant is the number of moles times a constant. And when looking at lots of different gases, this is what's amazing about this. It turns out that PV over NT, okay, I'm dividing both sides by N here, is a universal constant. And it doesn't matter what gas you're talking about. This is what's amazing about this. PV over NT is equal to R. Experimentally, you'll always get the same number, no matter what kind of gas you're talking about. This is how the ideal gas law is derived. So I started off this video by giving you the ideal gas law, or the equation of state. Now I've kind of derived it sort of through the back door by going through each of the particular cases and coming full circle. Okay, temperature needs to always be in Kelvin. N is the number of particles, and R is called the universal gas constant. So let's do, oh, by the way, for any thermal process, we can always then write this particular situation right here, where 1 is initial and 2 is final. Remember, we usually don't deal with changing N in problem solving in this class, but I'm writing the more general case for you here. Okay, so let's do a few more examples to round out this video. Go ahead and try this one. Okay, initial conditions, final conditions. Okay, let's see, in this case, PV over T, P1, yep, it's the same thing we've been doing over and over. I solve for T, I get 600K. As a sort of problem-solving insight, you should try to solve this one again using degrees Celsius and see if you get the right answer. I bet you don't. Okay. All right. This figure shows two what we call isothermal curves. I'll talk about them more later. It means that any 2 points on, for example, curve B are going to be at the same temperature. Okay. Which has the higher temperature? This is kind of an interesting question. Curve B, because notice that P and V have an inverse relationship. Recall from your math that a higher constant in the function a over x shifts the curve upwards. This is going to be important when in our next video when we talk about thermodynamics. So B is at a higher isotherm than A. So if we have a process where we go from B to A, it means that the temperature is dropping. Okay. Another example. Which straight line corresponds to the larger volumes? This is a P against T graph. It's line C because PV equals nRT. Okay. NR over V is the slope of the line. Since C's slope is less, its volume must be greater. Very clever, huh? Another one. As the temperature increases, is the volume of the gas changing? If so, how? This is again a PT graph. No, because PV equals nRT. NR over V again is the slope of the line, which is constant. Therefore, the volume is not changing. And example 9, a gas occupies, etc., etc. Try this one. So we're asking for the volume, and I get a volume of 0.375 cubic meters. All right. Again, the same procedure. Example 10, a little more difficult. Okay, I'm giving you the mass number, etc., etc. Okay. So a mass number of 4 means that 4 grams contains 1 mole. So 8 grams contains 2 moles. So here we actually are needing to use a numerical value for little n, the number of moles. Example 11. Try this one. Okay, I got 170 moles. Number of gas atoms, I got 1 times 10 to the 26 atoms. Okay, again, the bridge method, very useful